Hello, I'm Norman Wildberger. Today we're going to carry on with our applications of this concept of the dot product to planar geometry. So the dot product is a very foundational aspect of trying to build metrical geometry. But not just Euclidean geometry, but as we'll see also later, relativistic geometries and other geometries as well. They all ultimately rest on essentially something like a dot product. So here's the definition in the Euclidean case that we talked about last time. We're working in 2 dimensions with vectors. Here's a vector x1, y1, another vector x2, y2, and the dot product of those 2 vectors is this number here, the number x1 times x2 plus y1 times y2. And we discussed this formula for the projection of one vector on another. So the projection of w on v, let's call that u, is in this diagram here. Here's the vector v, and here's the vector w. And notice that they're positioned so that they're starting from the same point. So they're both sort of in standard position, starting at the origin in this case. Now we're interested in projecting w, this vector here, onto v. That means we're going to project it perpendicularly. You can think about sort of trying to find the closest point on v to the tip of w. And that's the vector u here. All right? So there's the vector u, which is the projection of w on v. And here's our notation for that, the projection onto v of w. And here's the formula for it that we defined last time. v dot w over v dot v, so that's a number, ratio of 2 dot products, times the vector v, so it's a multiple of the vector v. And here's another formula for it in the language of matrices, where we're thinking of this vector as actually being a matrix. Okay, so in today's video we're going to carry on with applications of this dot product. We're going to talk about the quadrants from a point to a line, and we'll introduce the idea of reflections, and then also rotations. And along the way it's going to be useful for us to introduce the point normal form of a line, which is another way of thinking about how to represent a line in 2 dimensions. And throughout we're aiming really for generality here. So although we're only talking about 2 dimensions and giving you pictures in 2 dimensions, the formulas and the thinking are designed so that they extend, first of all, to higher dimensions, and secondly to other symmetric bilinear forms. That's going to be a very powerful, flexible tool chest for us. So this is very foundational stuff for building metrical geometry using linear algebra, which currently is the best way, the most efficient way of setting up not just Euclidean geometry, but also other metrical geometries. So let's start with the point normal form for a line. So here's the plane with our usual x and y coordinates, and here's a particular line that we're interested in. And it's a line that happens to pass through this point, capital A. And we're told that it also has normal vector n. So here's a vector n, and this vector is a normal vector for this line, meaning that this vector is actually perpendicular to the line. Those are perpendicular directions. And also in this picture we have this vector A, which is the coordinate vector for the point A, just the vector from the origin to the point A. So when we use linear algebra in a situation, we want to convert points often to coordinate vectors from the origin, because then we can use the language of linear algebra, addition and subtraction of vectors and so on. Okay, we're also going to think about a general point on this line, which is represented by a coordinate vector x. So x with an arrow over it means a kind of variable vector which is supposed to be lying on this line somewhere. Okay, so the equation for this line is then this one here. Let's have a look. N dot x minus a equals 0. Why is that? Well, it's very simple. It's because the vector x minus a is just this vector from this point to this point. That's the vector a, that's the vector x, so this is the vector a minus x. And the condition that we want is that this vector be perpendicular to the normal vector n. And perpendicularity is defined in terms of our dot product. That's what it means for x minus a to be perpendicular to n. It means that the dot product of those two vectors is the number 0. Okay, we could rewrite this because we know that the dot product is bilinear. So n dot x minus a is the same as n dot x minus n dot a. And n dot a is a number that we could bring to the right-hand side if we want. So we could rewrite this equation in the form n dot x equals n dot a. So for example, the line through minus 1, 3, there it is there, with normal vector n equals 2 minus 1. There's the vector 2 minus 1 right there, little n. It has equation. All right, it's 2 minus 1, there's the normal vector, dot a general vector x, say with coordinates little x and little y, minus the coordinate vector of this point, minus 1, 3. That dot product should be 0. And when we expand that out, the 2 minus 1 dot xy gives us 2x minus y. And this other dot product, when we bring it to the other side, we get 2 times minus 1, that's minus 2, plus minus 1 times 3, which is minus 3, for a total of 2x minus y equals minus 5. That is indeed, looks like a reasonable equation, because if x is 0, then y is equal to 5, telling us that it's meeting up there, the y-axis at the point 5. And if y equals 0, then x equals minus 5 over 2, which is minus 2.5 down there. So this is the usual Cartesian equation of that line. Here is the point normal form for the line, involving a normal vector, a dot product, and an actual point or vector that's lying on the line. So now we have 3 different possible forms for a line in the plane. A parametric form, a point normal form, and the Cartesian form. Let's have a look at all 3 of them in this example here, actually describing this particular line. Alright, so the parametric form is x equals minus 1, 1 plus lambda 1 minus 2. So x here is an arbitrary vector. So this equation is telling us that a general point here has coordinate vector x given by minus 1, 1, which is this vector here corresponding to that point, plus a multiple of 1 minus 2. Here is 1 minus 2, and if we go a multiple of that from here, we're going in this direction here, or possibly in this direction if the multiple is negative. So we have a point on the line, the direction of the line, giving us the line itself. To get a point normal form, we need a normal to the line. In other words, a vector, like this one here, which is perpendicular to the direction vector. How do we get a perpendicular vector to 1 minus 2? In the plane, it's pretty simple. We take these 2 entries and flip them up, replace the x and the y with each other, and multiply one of them by minus 1. So for example, 2, 1 is a normal vector. If we take the dot product of this one with this, we get 2 times 1 plus 1 times minus 2. That is in fact 0. So that's why those 2 vectors are perpendicular, and this is a normal vector. Of course, any multiple of this vector is also a normal vector, because normal vectors are not unique, just as direction vectors are not unique. We can always multiply them by scalars, numbers, rescale them, and they're still normal vectors or direction vectors. So once we have the normal vector and we have a point on the line, then we can write down the point normal form. The normal 2, 1 dot, here's a general vector x with coordinates x and y. The difference between that and the point on the line, minus 1, 1, that dot product should be 0. And the Cartesian form for the line, the sort of familiar high school kind of formula, is 2x plus y equals minus 1. We can get that from this formula here by just expanding the dot product. to 2, 1 dotted with xy is 2x plus y. That's the left-hand side. And if we take the dot product of this vector and this vector to the right-hand side, we would get minus 2 plus 1, which is minus 1. So suppose that we started with a Cartesian form and you wanted to find, say, a point normal form. Well, what you would do is first of all try to find the normal vector, and the normal vector is pretty easy to read off from the Cartesian form. It's just the coefficients of x and y put together in a vector. So this coefficient 2 and this coefficient 1 together give the normal vector 2, 1. And the other ingredient is a point on the line. And for that there's a, well, wide range of choices because there's lots of points on the line to choose. The simplest thing is usually perhaps to let one of these variables be a particular value and then just solve for the other one. So for example, if x is 0, then y is minus 1. So the point 0, minus 1, which would be this point here, would be a possible candidate to choose. Or if we set y equals 0, then x would be minus a half. And so the point x equals minus a half, y equals 0 would be another possibility. So we could have replaced this minus 1, 1 with any other point which lies on the line, and we'd still get a point normal form. And how to get a parametric form? Well, once we have a point on the line, we just need a direction vector. And if you know one of these two forms, then you know a normal vector. And so you can go from a normal vector to a direction vector, basically the same way we went from a direction vector to a normal vector. Just take a vector that's perpendicular to the normal vector, then you're going to get a direction vector. It's the same idea. You just swap those two elements around and multiply one of them by minus 1. That's how you could get this direction vector if you knew the normal vector, either from the Cartesian form or for the point normal form. Okay, so exercise here for you. Play around with this. Find, say, other forms for, here's a line 3x plus 4y equals 2 in Cartesian form. So try to write down a parametric form and a point normal form for the same line. And you might like to graph it. And here's another line, the x equals 4, 2 plus lambda minus 1, 3. Graph that and write down point normal forms and Cartesian forms for it. Now let's drive an interesting formula for the quadrants from a point to a line. Very useful formula. So we have a line, say L, and a point, say A, and we're interested in saying how far this point is from this line. Yes, but what does far mean? Well, the way we're measuring in this system is by quadrants. Right? If we have 2 points, we're defining the separation between those 2 points in terms of quadrants, which is the dot product of the vector joining those 2 points with itself. And it's always a rational number if the 2 points themselves have rational coordinates. So geometrically what we'd like to say is, well, there's lots of points on this line, but we'd like to choose the closest point. Right? So if we drop a perpendicular from A to the line, we get some point down here, and it's this quadrants here that we really want to identify, get a formula for it. Okay, so let's suppose that we have some information about the point A and the line L. Let's say that the point A has, first of all, coordinate vector little a. So the vector here, that's the coordinate vector for the point A. That's one of the things that we know. And we will also suppose that we know this line L in a point normal form. So we know it has an equation of the form n dot x minus v equals 0. And we recognize that. That means that n is a normal vector for the line. So in this case here, this vector here, n, is a normal vector. And notice that, vectors can be moved around. They don't always have to be at the origin. So the vector from here to here is really the same vector as the same one translated here. Or in fact, we could translate it anywhere. It's still the same vector. So we put it here because it's convenient for us to do so in terms of our diagram. And the vector v is the vector from the origin to a point on the line. That's a particular point on the line, and here's our point normal form for the line L. Alright, so the key ingredient is to use a projection. We're going to project this vector here onto the vector n. So let's have a look what we're doing here. So we know that there's one vector v right there. There's the point A, there's the vector A. This vector in green here, going from the head of v to the head of A, is the vector A minus v. That's that green vector that you see there. And what we're going to do is we're going to project that vector onto the vector n. Now notice that these two vectors are emanating from the same point. So that's our usual diagram that we have when we're about to do a projection. So the projection of this vector onto n is, in this case, well, we just go orthogonally to get this vector u. So this vector u is the projection of this vector a minus v onto n. U is the projection onto n of a minus v. And the reason why we want that vector is because that vector is going to be the same as this vector here. So this quadrant is going to be the same as this quadrant. Whether we measure this or this, it's going to be the same thing. Now we have a formula for the projection. The projection of a minus v onto n. What do we do? Well, it's going to be a multiple of n. So there's lots of n's in the formula, but only one a minus v. There's an n dot a minus v in the numerator, and then there's an n dot n in the denominator, and then we're multiplying all of that by the vector n. So that's an expression for this vector u. And the quadrants that we're interested in, let's say, call it q, is the quadrants of that vector u, which by definition is u dot u. So we have to take this expression and we have to dot it with itself. Alright, you have to remember that this is just a number. Okay, this is some number times the vector n. So when we take the dot product of that with itself, we're going to get that number squared times n dot n. So we have over here n dot n, and here's this coefficient, all of that squared. And now let me just rearrange that just a little bit, noting that this n dot n factor down here in the denominator is squared. And there's a similar factor up here in the numerator. So there's a bit of cancellation there, and we just get a single n dot n now in the denominator. And up here in the numerator we have n dot a minus v, all of that squared. So the answer is a number, and it's a quite nice formula that I want you to stare at for a little while and become familiar and comfortable with this formula. All right, so this is a formula for the quadrants between this line and that point, and it's a number that involves three ingredients: the normal vector n, should be a vector over there, the vector a, which is the coordinate vector of the point that we're projecting from, and the vector v, which is a vector, coordinate vector for a point on the line. And now note, the quantity that's in brackets here, n dot a minus v, is very similar to the equation of the line. The equation of the line is n dot x minus v equals 0. So suppose that the point A actually lied on the line. In that case, we'd replace x with a, n dot a minus v equals 0. That means this would have to be 0. That's good. That's telling us, it's a check that's telling us that if the point A lies on the line, then in fact this numerator here is 0, and we're getting a quadrant of 0 as we should. Otherwise, we're obliged to take this number and square it and divide by n dot n. And the effect of this n dot n is just to account for the possible renormalization of a line. So if you take a line like this with a normal vector n, the normal vector n is not unique. Someone else can come along and replace n with 6 times n. You don't want your formula for the quadrants to change if the n is replaced with 6 times n. Well, in here, if you replace the n with 6 times n, there's a 6 that will come out here, and with the squared, there'll be a 6 squared coming out of the numerator, but there's a 6 squared that will be in the denominator to cancel so that the thing is still independent of scaling of n. You can think about that's the reason why there's an n dot n here. So the formula may look a little bit complicated, but all what you really have to remember is that it's essentially the formula for the equation of the line itself, where you replace the general point x on the line with a particular point A in question that you want to measure how far away it is from the line. And you're squaring that formula and normalizing by n dot n. Now, in most texts in linear algebra, you're not going to find this formula. You're going to find a much inferior formula. You're going to find a formula for the distance between the point and the line. In the 20th century, people thought that distance and angle were the right ways of thinking about metrical geometry. But now in the 21st century, we know better than that, don't we? Especially those of us who have been learning rational trigonometry and watching the videos in this channel. So we don't want to think about distance, because distance involves a square root. The distance is just the square root of the quadrants, just the square root, as long as you're able to calculate a square root, which in fact generally requires an infinite amount of processing. The square root operation is something that goes on infinitely, as I've mentioned many times. And we don't want to engage or force our computers to perform an infinite number of tasks before we get an answer. That's why we're going to stick with the quadrants, which is completely algebraic. There's no square roots in sight. But if an engineer says, yes, okay, but what is actually the distance? I want to make a measurement. Then we'll just take an approximate square root. We'll get out our calculator, press the square root button, get some number to 5 or 10 decimal places, and give that to the engineer. The engineer knows it's not an exact answer. He doesn't care. We as pure mathematicians, we do care. Right? So we're going to work theoretically with the quadrants, but if someone really wants a distance, well, we'll take an approximation and give it to them. All right, so this is a very useful formula that basically takes the equation of the line and extracts from that the quadrants from a point to the line. All right, so let's look at an example or two. So our first example, we have the point A, which is 1, 2, and the line, which is given in point normal form by 3, 4 dot xy minus 0, 1 equals 0. The meaning, here's the point 1, 2, there's the point A. The line is this one here. It's got normal vector 3, 4, something like that. And it goes to the point 0, 1, which is right here. We're interested in the quadrants between this point and this line, by which we mean this vertical quadrants that we get by dropping a perpendicular from the point to the line. Okay, so the formula tells us that the quadrants is what you get when you take this equation and replace the unknown xy with the particular point 1, 2. So we get 3, 4 dot 1, 2 minus 0, 1, all of that squared, and we have to normalize by the quadrants of the vector n. 3 squared plus 4 squared. Okay, so there's a 25. And then we're going to get 3, 4 dotted. Well, we might combine these things here to give us the vector 1, 1. There it is there. When we take the dot product of 3, 4 with 1, 1, we're going to get 3 plus 4, which is 7. And that 7 has to be squared. Remember the square here. For a total of 49 over 25. Now in this particular case, we see that we could take a square root of this thing, because this happens to be a square. So in this case, the notion of the distance from this point to this line is in fact a valid notion. In general it's not, but in this case it happens to be. And here's the more familiar Cartesian equation of that line that you just get by expanding this out. 3x plus 4y equals 4. Here's another example. The point A is the point 5 minus 2, which is right here. The line is the line x minus 2y equals 5, which is right here. Now it's not given in terms of point normal form, it's just given in terms of sort of a Cartesian equation, but we could essentially get it in this form by bringing everything to one side, so that this whole stuff here is on the left-hand side, there's a 0 on the right-hand side. So that would be x minus 2y minus 5 equals 0. And the formula tells us we have to substitute the coordinates of a into x and y. So 5 minus 2 times minus 2 minus 5. That's the equation of the line with x and y replaced with 5 and minus 2. We have to square all of that, and we have to normalize by the sum of the squares of the coefficients of x and y. In this case, 1 squared plus minus 2 squared. For a total of 5 minus 5 is 0, and then there's a 4 in there. 4 squared is 16 divided by 5. So here this is not a square. So in this case, the distance is not defined. No distance, but there is a quadrant. There's always a quadrant. The quadrant from this point to this line is 16 over 5. Now we're going to introduce the idea of a reflection in a line. The lines we're going to consider here are relatively simple ones. They're all ones going through the origin, which makes the formulas a little bit simpler and easier to remember. So we'll start with a vector v, which we'll assume is non-zero. And that defines a line, the line v dot x equals 0. The line with normal vector v, which passes through the point 0, 0. Here it is there, if that's the vector v. And now we want to define reflection in this line. Okay, this line. Sometimes we might call this line v perp, okay, because this line really consists of those vectors which are perpendicular to v. And we want to reflect in this line, thinking of it like a mirror, so that this point here is reflected here, so that this point here would be reflected here. A point here would be reflected here. So the idea is that we're reflecting, we're going perpendicularly to the line, and then an equal amount on the other side. Okay, how do we describe that? Let's have a look here. Here's a general vector w. We want to go over here. This is the reflection, say r sub v of w. And how do we know which direction to go? Well, this direction here is really in the direction of v. And its size is exactly determined by a projection, because this vector here is exactly the same as the projection onto v of w. So here's v, here's w, here's the projection of w onto v. Go perpendicularly down here like this. That's the projection of w onto v. And that vector there is the same vector we're using here, and the same vector that's over here too. So the geometry tells us that this projection vector, r of w, or if we want to be more specific and show that it actually depends on v, we'll write r sub v of w. So it is given by what? Well, here's the vector w, and we have to subtract 2 times this projection vector. Right, here's the projection. If we subtract it once from here, we're going to go here, and if we subtract it once more, we're going to get down to there. That's the meaning. W minus 2 times the projection onto v of w. And now, just to be specific, I'll remind you what the projection is. The projection of w onto v is v dot w over v dot v times v. So this is a very important formula here. It's the reflection of the vector w in the line v perp, the line that's perpendicular to the vector v. Now somebody might come along and say, well, there's also another possible reflection that we could do. Here we have the vector v. Couldn't we also reflect w in the vector itself? In other words, sort of go towards v and then an equal amount the other side. Well, that's another type of reflection that we might find useful. And if you stare at the geometry, I think you'll convince yourself that, in fact, this thing here, let's call it t sub v of w. So the formula is just the negative of this one. 2 times p sub v of w minus w. And to see that that's true, here's one way of thinking about it. That if you take the vector w and you take this vector, whatever it is, then the vector p sub v of w, this vector here, is exactly halfway between them. So it's the average of those two vectors. So if you take this vector w and put it to the other side and you divide by 2, you get p sub v of w. It's a way of remembering what the formula is. And in terms of p sub v of w as our usual formula, we can write that explicitly as 2 times v dot w over v dot v times v minus w. Okay, and so your next exercise is to, I guess it's number 2, is to find matrices for these linear transformations. When the lines go through the origin, then this is a linear transformation of w. Okay, it's linear in w. And that means that it has a matrix for it, as we've discussed in the first half of this course. So your exercise is to find matrices which encode these linear transformations, r of w and t of w. So here's w, here's r of w, and here is t of w. And if we want to keep track of the dependence on v, the fact that this actually depends on v, we'll put an indices of v down there. You will notice that I'm trying to stick with formulas that involve the dot product. So the dot product is the central operation that we're using over and over again to define these various concepts. We're doing that because of the generality that we have in mind, because we're going to eventually be generalizing to higher dimensions and also to different symmetric bilinear forms. Okay, now I have an important definition. A linear transformation, say M, from our two-dimensional vector space to our two-dimensional vector space. We're just talking about column vectors with 2 entries. Such a linear transformation is called an isometry precisely when M of v1 dot M of v2 equals v1 dot v2 for any vectors v1 and v2. So you have any 2 vectors v1 and v2 and you compute the dot product, you get a number. And then you apply this linear transformation M, okay, which can move the vectors around to give you 2 new other vectors. If the dot product of those 2 new vectors is the same as the original dot product for any v1 and v2, then this linear transformation is called an isometry. What it's saying is it doesn't change the geometry. These are very important transformations. They keep the geometry the same as it was before. So, theorem, which we might call the reflection isometry theorem, that for any non-zero vector v, this reflection r sub v that we defined, it's an isometry. Reflection is an isometry. Let's give a proof. Okay, so what do we have to do? We have to verify that this condition is satisfied for r sub v. So we need to make a computation. So given vectors v1 and v2, we are now going to compute r sub v of v1 dot r sub v of v2. And hopefully we'll get just v1 dot v2 at the end of it. Alright, what is r sub v of v1? Here's the formula for r sub v, acting on v1. So there's v1 minus 2 times v dot v1 over v dot v times v. Right, the v1 only appears in that spot there. And r sub v of v2, exactly the same thing, but there's a v2 here and a v2 instead of v1s. We have to take the dot product of this vector with this vector. Now this vector is actually a combination of 2 vectors. It's a combination of v1 and this multiple of v. This one here is a combination of v2 and this multiple of v. We have to use the bilinear property of the dot product. The fact that this dot product is equal to, by the bilinearity, it's sort of like the distributive law, it's v1 dot v2, and then there's this one here dotted with this one. So minus, well, this is just a number, so we'll pull that out front. And when we pull that out front by the bilinearity, we still have v1 dot v. There it is right there. Another term in the expansion is this vector dotted with the v2. So again, there'll be this factor, minus 2, v dot v1, v dot v. And then there'll be v dot v2 here. And finally, we have to take the dot product of this with this. Okay, there's a 2 times 2 is 4. The two minus signs give us a plus. This is a number, which I've reproduced here. And this is another number, which I've reproduced there. Those numbers pull out by the bilinearity property of the dot product. And what we're left with is a v dot v at the end. Okay, what happens to all of this? I claim it's just v1 dot v2. That it's really just amounting to this first thing. That these three things cancel. Let's see why that is. Let's have a look at this last one. Okay, there's a v dot v1 in the numerator, a v dot v2 in the numerator, and this v dot v will cancel with one of the v dot v's in the bottom, leaving us with a single v dot v in the bottom. That's the same that we have here. We still have v dot v1, v dot v2, and a single v dot v in the bottom. And it's the same as what we have here. So after we've done this little cancellation, these terms here are all the same. And the fact that we have minus 2 of them here, minus 2 of them here, and plus 4 of them means that they total up to 0 very nicely. And we're just left with v1 dot v2, so this thing is an isometry. And as an exercise, you can show that T sub v is also an isometry. It's almost obvious, but just think about that too. Right, so here are some exercises for you. First of all, show that one of these reflections, r sub v, is what we call an involution, which means that if you do it twice, you get back to where you started. Or algebraically, r sub v squared equals the identity. And what that means is that if you take any vector w and you apply r sub v to it, and then you apply r sub v again, you get back to w. Geometrically, this is sort of obvious. I mean, we're thinking about the reflection as being something that reflects in the line. So if we start with a w here and we reflect it first in this line, and then we reflect it again, well, we should get back to where we started. But I want you to prove this algebraically. Next exercise, describe explicitly the linear transformations r sub 1, 2 and r sub 3, 1. Okay, just draw some diagrams so you see exactly what those reflections are doing to general points or vectors, as well as this composition. So here's a composition of two linear transformations where you do one and then the other. And I remind you that our convention is that we'll do this one first and then we'll do this one. And I've just reminded you here. So if you have two transformations P and S and we're taking the composition P composed with S of V, it means first you do S, so you take V and you apply S, and then to that you apply P. So this just gives you some practice in what happens if you do one reflection and then you follow it by another reflection. I want you to have a physical understanding of what that's doing. And here is then an interesting theorem, which we might call the reflection conjugation theorem. I want you to prove this. Okay? So prove that if we have vectors v and w, and if it happens that r sub v of w is, say, a vector u, then if you take this composition, r sub v, r sub w, r sub v, and that means first you do r sub v, then you do r sub w, then you do r sub v again. That's the same as just doing r sub u. Okay, so this is a very important fact about reflections. So please make some diagrams, convince yourself of it geometrically, and then see if you can deduce it algebraically. Okay. Everything ultimately has to be proven algebraically. We cannot refer to diagrams for proofs. The diagrams are there to help us understand things. The proofs always have to be written down and ultimately just come down to algebra, using always the fundamental properties of the dot product. Great. So we have some experience with reflections, which are fundamental kinds of linear transformations associated to metrical structure. In other words, to Euclidean geometry. Now we're going to introduce rotations, which are usually maybe sometimes considered a bit more fundamental. Our point of view is going to be that rotations are a little bit less fundamental than reflections. We're going to start off with the question of, well, how are we going to define rotation in the first place? Before we start making computations with rotations, we should say, what are they exactly? What is their definition? And it's not enough to say, well, it's what you get when you move something around. You take the whole plane and you rotate it. Okay. Yes, we have a very good physical visualization because our brains are very good at rotating images in our minds and recognizing when images are rotated. We're biologically well suited for that. But we cannot use that as a replacement for logical definitions. Okay. So the approach that I'm going to take here is quite different from most linear algebra texts. And again, we'll have lots of advantages. So in a little while, we're going to be talking about relativistic geometry. I'm going to give you a bit of an introduction to that, and via linear algebra. And we're going to see that this kind of definition just fits very well with that, and also in higher dimensions too. Okay, so the definition really ought to be independent of any prior theory of Euclidean geometry, especially since these days Euclidean geometry is rarely ever laid out correctly. Like rational trigonometry is really the only way of setting it out logically correctly in the modern era. Now, we don't want to use physical intuition. We don't want to rely on our physical understanding. And we don't want to invoke transcendental quantities, which are very dubious to actually compute with, things like angles and transcendental functions. So what's our definition? Our definition is a rotation is a composition of two reflections. That's all. You have two reflections, you compose them, what you get is called a rotation. So, an example. Here's a vector v1, here's a vector v2. Here is the perpendicular line to v1, might call that v1 perp, and here is the perpendicular line to v2, I might call that v2 perp. So we can think about reflection r sub v1, which is the reflection in this line v1 perp. Sends that point to that point, sends that point to that point, sends that point to that point, and so on. We can think about the reflection r sub v2, which is reflection in this line. Sends this point to this point to this point, and so on. So here's a rotation. If we compose r sub v1 with r sub v2, and I remind you that means do this one first, and then do this one. Then, by definition, that transformation, they're both linear transformations, so that composition is going to be a linear transformation too. That's what we're going to call a rotation. Okay, technically it's a rotation about the origin. Okay, so it's a rather special kind of rotation if we want to be precise. It's also possible to talk about more general rotations, just as it's possible to talk about more general reflections. Right now we're just talking about reflections in lines to the origin and rotations about the origin, which are the simplest kinds. Okay, what does this actually do? Let's say you have a vector, say this one here, and we reflect it using r sub v1. What happens to it? Well, we reflect it in this line here, and so that this vector goes to this vector. And now we apply r sub v2, and that means we're reflecting now in this line, so that vector goes to that vector there. So the cumulative effect is to take this vector as the input and send it to this vector here. So it ends up being a rotation. You can test it out for other vectors and convince yourself that what's happening is that the whole plane is being rotated around by that much. Now we're going to introduce a bit of notation. So we'll say that this composition, we'll write it as r sub v1, v2. So we can use the same letter r for rotations and reflections, just telling us that the rotation is kind of, well, it's a pair of reflections. It's built up from reflections. First the v1 reflection, then the v2 reflection. And there's a question here. There's lots of things to talk about rotation. We'll talk about them later in a little bit more depth. But at this point here, you should be aware that the same rotation can be described with other pairs of vectors. You might like to think about that a little bit. Alright, so in our next video, we're going to have a look at circles, okay, which are naturally associated with rotations and very important aspects of Euclidean geometry, of course. And we want to introduce circles without any compasses. No technology like that required. We're just going to do everything algebraically. And again, the centerpiece is the dot product, and we're going to set things up so that we're in the future going to be able to talk about relativistic circles just as easily, or almost as easily, as Euclidean ones. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.